Okay, all right. So this will be the third installment of the Vulkan with Rust series that we've been talking about. And I think, so today, hopefully, this is one's going to be a short stream. And primarily, I want to cover CUDA versus Vulkan, but also talk about, because this was, this is about some of those questions that, you know, you guys were asking about, saying why Vulkan, first off? Why do you think Vulkan is very important? And so here goes. This is the first part of that stream where we will be discussing, or rather, we will be comparing Vulkan against the other sort of GPU programming APIs that I talked about. Things like CUDA, things like you can have AMD's version of ROCm, which is, I think it's pretty similar. Then you also have something called HIP, which is um, it's called heterogeneous. Sorry, what is that? Forgot. HIP uh, programming. It's actually from AMD. Yeah, heterogeneous computing interface for portability. So pretty long name, but this is again a C++ style CUDA-esque, you could say, API or framework that you can use to talk to your GPUs. And this is not, so CUDA is proprietary to NVIDIA GPUs, and ROCm, I believe, is for AMD. Now you can have something that's heterogeneous that works across. This is akin to something like OpenCL. So I talked about all the different APIs in one of the previous streams as well. I talked about, let me see if I can sort of find it. Um, so, um, well, think, um, single source. I think this one. Right. So I talked about in the past in when I was covering um, another wonderful crate called kubecl. Talked about the single source model versus the shading language approach. So Vulkan pretty much fits in this space where you don't have a single file in which you actually write your host code and your device code or your GPU code. You actually split them into two parts. You write your device code in what's called the shading language, any one of these languages, depending on uh, which platform you're working with. So Apple has Metal, HLSL is used by DirectX, which means that's Windows, and then GLSL and GLSL or WGSL or WGSL is the up and coming standard used by web GPU. And GLSL is something that is used across the board, primarily is used in Vulkan as well. There's also another language by NVIDIA that's called Slang. That's little, at least it was made public recently, but that's also another shading language. But effectively, two types. You can have the single source method, or you can have the split where you write your device code in a separate language, and then you write your host code in whatever programming language you think is fit. And Vulkan sort of fits into the second category, all right? And yeah, these are the other options: CUDA, ROCm, SYCL, etc. But the reason we're not talking about all of them is because it's very simple. There's only one API that's really, really popular, which is CUDA. Um, and that's kind of why you hear a lot about, NVIDIA, uh, because you might have been wondering, why is there only one GPU company that's being talked about? And that's a lot to do with this particular part. Is a lot of people know how to work with CUDA because CUDA came out many, many years ago, and it's what you'd use in many other areas where this sort of parallel compute is required, like HPC or simulations or a whole bunch of different things. You technically, wherever you use large scale, uh, you have a large deployment of GPUs, you probably want to use CUDA because you'd find a lot more people who know CUDA. Uh, and ROCm and HIP and SQL and all of these are uh, they were they came into existence post CUDA is how I know it. Yeah. So long story short, that's why I thought I'd pick, not just because of that, but that's also because there were a couple of questions as to why. So CUDA versus Vulkan. The one thing that we'll quickly get through is Vulkan is actually much lower level than CUDA. It's what I would call, and I'll give you examples of that as well. So in CUDA, when you actually write your, so I think I should have like an example over here. So let me see. Uh, so yeah, there's this nice little playground called Lead GPU. If you go here, you'll be able to quickly, spin up some. I hope you can see this. Yeah, you'll be able to quickly spin up, without having to install CUDA on your machine. It won't run on my Mac because it is NVIDIA specific, and the Mac does not have, at least the Apple Silicon, you know, computers do not have an NVIDIA GPU, so you can't run it. You can pretty much go ahead and just use one of these services. Lead GPU, I believe, is a very good one, where you can pretty much just run your CUDA programs in the cloud, and you can get your answers back. So, and you can choose your GPUs and stuff like that, which is all great. Which I am not going to do right now. Just run it, see that it works. And yeah, you're not going to get any, you know, real calculation over here. This is just printing uh, what you'd call a message to the screen. And you would see that this is what I talked about when I said both your, this is your kernel code, and or rather, this is the actual GPU specific code that runs on the GPU. This is your kernel, right? It's marked with this um, identifier or keyword. And then this is what your host code is, everything that's inside the main function, right? Uh, but if you looked at our previous implementation, you'd see that, hey, this thing looks massive, man. Look at this. This is it to just print something uh, via the GPU. It's a useless thing to do, but yeah, you want to print it out. Just a hello world kind of an application, you can go ahead and do that. So it will go ahead and effectively, they'll be spinning up multiple threads to go ahead and write this, or rather copy this, or whatever it is that it's doing over here, which is, as you can see, CUDA mem copy to symbol, which is, I'm not going to explain this. This is going to take a while. I just want to quickly say that the GPU will be able to print this message out for you using this particular kernel. But in our case, and the last time when we actually talked about a command, talked about Vulkan, you saw that this is the massive. So, this is all CPU code. You don't see any GPU code anywhere, right? You don't see any of it anywhere. It's all CPU code at this point. And the last time what we did was we were simply trying to, let me see if I can pull it up. We were simply trying to do this much, which is we wanted to go ahead and transfer, we wanted to allocate some memory on the GPU, and then we wanted to write 4 bytes in a repetitive fashion into that allocation, and then read it back, all right? A read back part is not specifically recorded over here, but the first part, which is want to go ahead and start recording this command so that that command can be processed by the command processor of the GPU. as I mentioned the last time, you have a command processor in the GPU, which is basically a very good microcontroller or a high performance one, or an actual processor itself that's going to be pulling stuff from the queue or commands from the queue and then processing them. And then the entire thing is all those commands are present in the command queue. All of those pieces I've covered in the second episode. So just taking that part here, you will see that you've got a command buffer. And the only thing I'm trying to do over here is fill that buffer with these 4 bytes. And command fill will basically do however big your command buffer is, those 4 bytes will be, you know, will be repetitively written to that buffer that you've allocated. And that's it. That's all we're doing over here. But there's a lot of ceremony that you see over here that happens. And this is what I mean by Vulkan being very, very low level and explicit. Because what we're attempting to do is effectively a very low level command. It's actually part of what's called a transfer command. And CUDA does not really, I mean, you can do that. You can do exactly the same thing that you've done in Vulkan in CUDA, but you don't have to go through all of that. You don't have to set up so many data structures, and you don't have to like walk through each little piece. And that's why Vulkan is a lot more explicit. And by its very definition, if it's something is very low level and explicit, you have a lot more control. That means you can get a lot more fine grained with what you want and how you want it to happen. And that's not the same case with CUDA. The first thing is CUDA is only for um, compute. That means if you're basically doing things like machine learning workloads, or you're doing some kind of other kinds of compute specific workloads, that's all you can use CUDA for. You can use the graphics portion of it. Vulkan is an API that does both. You can use it for graphics and you can use it for compute. You can also use it for ray tracing. And that's exactly what I'm trying to say. So the whole thing about Vulkan is it's explicit and low level, which is why I highlighted the two most important elements. In CUDA, you can see that, where did that go? You'll see that if you just look at this, the CUDA specific functions that deal with the GPU, CUDA malloc, this allocates memory on the GPU. CUDA memcopy to symbol. You're trying to copy um, some value into some other place once you've done the allocation on the GPU. And then you're going to go ahead and do a read back. That means you're going to get the result back. This is a CUDA memcopy. So all of this stuff, all of these calls that you see, these are all functions that you have access to that will allow you to interact or program the GPU. But that's not as straightforward in Vulkan. So if you wanted to do that, basically do this read back stuff, let's at least look at that. Let's see, let's just go down. So here is where we submit the command. So the command's been submitted, and then you're expecting data back, right? So when you're expecting data back, um, so let me see where I can. Yeah, so the allocation that you've already made over there, you want to map that into your host visible data structure. So by the way, it sort of looks very simple, but because we're using a very specific allocator that made things simple for us, it wouldn't be this simple to read that stuff back. You'd have to do a little more ceremony, but all that's hidden right now. So that's fine. But the fact is, you can't do, I mean, if you wanted to write it yourself, you could do so in Vulkan, but here you'd not bother because you've got the CUDA, you know, helper function that you need to do to copy from host to memory or memory host to device or device to host. So it's a lot more what you'd call implicit. A lot more stuff is being done for you. And that's why CUDA is very implicit. So that's the first thing. And the second thing is when I talked about queues, in the Vulkan side of things, you would never really see them in CUDA. They will show up as something called streams, right? But you don't have things that are very specific. First off, you can't do a lot of things like queue selection and management at a very fine-grained level in CUDA, although they mean the same thing. CUDA lets you get away with, simple things, simple stuff. Uh, if you want to deal with multiple queues, you can use this concept of streams, and then you can go ahead and schedule work or commands onto that. And you never see even the word command in CUDA. It never shows up. You only keep dealing with these CUDA APIs like CUDA mem copy, etc., etc., etc. Same thing again over here for synchronization. We This is a good example because we actually did this. If you see this over here, you have something called a fence that we have to create. It's a synchronization object. Once we submit that transfer command to the GPU, we want to wait so that the GPU does the work and then gets back to us. That's all asynchronous. That means we don't know when that's going to complete. So we want to ensure that when you do complete, just don't go forward without um, letting me know that you've done this particular command is completed. So that part is what we are sort of explicitly calling out over here and saying, and when we submit that command to the queue, we're doing that. Even the submission part is not there in CUDA. You won't have like submit to queue and stuff like that because the concept of a queue doesn't exist, but a stream does exist, which is sort of similar. Um, so yeah, so this is the key point that I wanted to sort of bring about. And I picked some of these aspects when it comes to the programming model or queues or command buffers or synchronization, etc. But as you go down the list, you'll find a whole bunch of things that are different. The high level view is Vulkan is explicit and very low level. And that's why when you start working with Vulkan and you see, okay, like usually people say this when they're drawing their first triangle Vulkan, it's like, I'm pretty sure that the Vulkan's never coming. And sorry, the triangle's never coming because what the hell? It's going to take you 500 or 1,000 lines to just do all the ceremony and get everything ready. And then you will get some output that you were waiting for. Some of the other APIs like Web GPU, etc., sort of simplify that. CUDA in the compute world simplifies that for NVIDIA. So there's all these APIs that do very specific things, but Vulkan is the only API, at least that's I'm aware of. I think DirectX is also very similar to Vulkan, but I have no knowledge of that. But Vulkan is the only open source API that allows you to be as explicit as you want and as low level as you can, depending on what you want to do. Allowing you to do whatever you want to do exactly the way you want to do it. That's how I would put it. All right. So that's in a nutshell when we talk about CUDA versus Vulkan. So the other part, I've also mentioned things like the CPU will be doing things like recording commands into the command buffer in the last in episode 2 of the series. That's not something that you do in CUDA. This is all automatically managed for you, right? So, and you have inbuilt variables like block, index, thread index. All of these things are provided to you. So it's higher level relative to Vulkan. But in Vulkan, you can actually do your own thread management and your own memory management. You can have multiple threads that are recording commands into command buffers that will be submitted to multiple different queues, um, so that you can have a lot of parallelizable, like you can really parallelize your workload a lot more and be a lot more fine-grained about it. But the cost of that is, there's a lot of complexity that comes into the picture, especially things like synchronization. They start to creep in. And that's where you say, okay, I need to ensure that my command in this queue is done before, this other command in this queue that I submitted in this particular compute pass needs to complete. All these things need to be sort of managed by yourself. Yeah. So that's the CUDA versus the Vulkan API. And Vulkan is effectively what I would say, and many would agree with me as well, is to say the the future, actually. You can put it that way. Um, and one passing note I'd say is you might be wondering, okay, what about Metal? Because you're working with a Mac, and the official GPU programming API that Apple offers is Metal. So Metal is also low level. Um, it's also explicit, but not as explicit and not as low level as something like Vulkan. Case in point, I can give you an example as we go through it. We'll be doing so. This was the first piece that you guys wanted had questions about, and the second one was, I want to put all of these together in some visual manner. So I was able to figure out the debugging part. So we've done the transfer. We've done that. What we would call this. What is that? Yeah, we've done this part. We've recorded a copy command to copy data into a command buffer. That's kind of what we're doing over here. So this single command that was submitted, usually nobody submits a single command in a command buffer and asks the GPU to do it. That's just nonsense, because the whole idea about GPU is it's not good at latency sensitive compute. It's very good at throughput. So it hides all the latency stuff that you have to deal with. So if you wanted to use a CPU uh, for just the copy, it makes a lot of sense, because um, it's it's a simple copy command. It's a single command. You can go ahead and do it. But if there are many, many copies that you want to do, and there's many, many such operations that you want to do, then that's where your GPU can do all of these things in parallel versus something like a CPU, which has, which is very fast when it comes to the clock speed and the latency part, but can't compete with the GPU in terms of sheer throughput, right? So just, I just want to call that out, because we're going to be examining what is called a GPU trace. We're going to be tracing the command recording and the command submission, and what the GPU does, and we'll also see some profiling information as well. All that part with just a single command, so that it's a lot more easier. The first thing is, I didn't know anything about Apple's ecosystem, where how do you do this with the Metal, within the Metal world? Because at the end of the day, Vulkan, Vulkan on the Mac is called MoltenVK. So when you write all this stuff, it translates all of these API calls, like, for example, begin command buffer or whatever all this stuff is translated to the Metal specific, API. Because Apple's not going to let you do your own stuff on Apple, right? So you'll have to do all that stuff. It's so there's a translation that's actually happening, but it's actually a super low cost translation, because apparently performance is pretty much on par with Metal. Um, so we'll see that. We'll just see, what happens when you do this in uh, in actuality, in reality. Sorry. So in order to do that, the first thing that we need to go look at is, um, if you see this, there's the MoltenVK runtime user guide, and I found this piece that says debugging your MoltenVK application. All right. So long story short, you just set some, uh, um, you just set some environment variables, specifically a metal capture enabled, then the MoltenVK config auto capture thing enabled, and you also enable this one, which will tell you exactly where your file is supposed to be. Your GPU trace file should be put. So I think I've not removed them, so I'm assuming that I've already, yeah, let me just check if it's already there. It's not there. So it looks like I'm going to have to export this. So I can go ahead and do this, because I've already sort of done this. This is going to be the name that I give my GPU trace file. And I'm just going to say command fill test. Yeah. So maybe just put an underscore there. Right. So once I do the export, all these variables should be, yeah, in place. So now everything, once these environment variables are set, I just simply go ahead and do cargo run like we did last time. Um, and we get the output. That's great. But if you go back to our visual, our VS Code instance, you'll also see this. You'll see that we've captured a GPU trace. We've basically managed to go ahead and uh, all the stuff that we wrote, basically all the setup, all of that stuff, MoltenVK translated that to metal, the metal calls that need to be called, and submitted work to the GPU. And the GPU actually went ahead and ran it and produced the results that we're seeing on our screen over here. All right. So how do you actually sort of work with the GPU trace file? Partly, I didn't know that. I had to actually Google it. So the first thing that we need is we need Xcode, and then we simply go ahead and uh, open the file. So for me, that's yeah, it's a little further out. So I'll just open that. And the moment I'm done with that, I want to also do profiling. So you have to check this box if you want profiling information, not just debugging information. So that's it. Now I have the whole thing. So if you see this, it's going to be doing profiling. But before we get that, I don't know how to make the font size bigger. So bear with me. I presume there is something, there is a way to do this, but I have not figured it out. So there's one command buffer. There is one compute encoder. So this stuff, this encoder stuff, is exactly what is not present in the Vulkan API. So you generally, if you want to write to or want to record your commands into a command buffer, you do that directly. You don't go ahead through an encoder. That abstraction is something that Metal provides, right? So this is the idea that I was saying that Metal is a bit higher level than um, Vulkan, right? And then you can see that there's one dispatch call, the one single command that we submitted to the queue. That's called the dispatch call. So that's the information that you have. Then we'll click on the show dependencies part, and then it also gives you some profiling information, performance time. So how long did the GPU actually take? Because if you see here, where's that? You see this? Uh, we are talking about some 35 milliseconds and something out, which makes no sense, right? You're wondering why does it take so long? Well, that's because that's the read time and the print time and all of that stuff, which is that's not an accurate uh, description. It's actually this is the amount of time, right? That's the amount of time that it took for the GPU to do the work that you've submitted, which is microseconds, 3.92. Right? The first thing that you can do is actually let's go ahead and look at the performance part. You click on that. Here's the first thing that you get. You get all of these things that you see over here. You're not going to see much of a graph over here. The reason for that is because we're not doing anything. We're not we're not utilizing the GPU and all of that stuff. All we're doing is, copy command. That means we're copying data between the GPU and CPU. So that's what you're going to see over here is the amount of time that takes, the read bandwidth and the write bandwidth. And I guess that's kind of what you'd see. There's not much. Maybe some cache misses is what you'd see, depending on how much of how many registers we're using and etc. Because we're doing some copying and stuff. So these are what you'd call GPU counters. Counters, like any other piece of hardware, are effectively, you can say, specialized registers that are baked into your hardware that allow you to monitor specific events. So every time an event happens, a counter is incremented. You can go ahead and then pull that information and then use it for performance analysis, et cetera, et cetera. Here's the thing, you can do it offline. That means after you've done your computation. And second, you can also do it real time, et cetera. You can calculate the amount of time it took and all of that stuff, the way that's being calculated. The way you do that is, although you only have a counter, how are you calculating time? Well, you put a timestamp when you submit stuff, and then you try and figure out, okay, the timestamp was this when we recorded it, this when we submitted it, this when it was executed, and these are the number of counts. Basically, there's some maths that's involved, and then you can figure out a bunch of things. So if you hover your mouse around over here, you'll be able to see, where's that? Yeah, you'll be able to see some descriptions over here that's saying, what does this counter actually measure? It measures how much memory in gigabytes per second are read by the GPU from a memory external to the GPU, potentially device memory. And if you don't want this graphical view, you can simply go to this view and then look at it. And then you can see the pressure on the memory. If you see the most amount of work or any kind of numbers only showing up in memory, because that's pretty much what you're doing. There's nothing happening over here and stuff. All right, so this is the first part. Now, that's performance counters, and you can use them in various ways to figure out stuff. And then there's this stuff that took me a while to understand that, it's actually telling me that you're probably not using the API properly. And this is not the Vulkan API. We're talking about the Metal API. And it gives you a nice little explanation over here. It says your application created a Metal compute pipeline state object during GPU work. Okay, you should not be doing that. Please create them up front, is what it's saying. We look at that. I'm yet to figure out what is going on. But yeah, and then all the stuff is great. And then you can basically debug effectively what's happening with your GPU workloads. That's kind of what this is all about. That's why it's called the Metal Frame Debugger. I think they should just call it the Metal Debugger, because frame presumes that you're dealing with only graphics. No, we're just dealing with compute over here. All right. So the other thing that you can do is you can group the entire flow that you went through. You can either group it by the APIs that you called, or so for example, let me see if I can just expand this. So you see this is the buffer creation. And then this is the kernel command fill buffer command. That is this one. And then there's the pipeline state that you were creating with this particular kernel function. And then there's the qsubmit. You can expand that, and then you can start looking at that. But the more I looked at it, I preferred the pipeline object phase, because it tells you exactly what you're doing. You've created a compute pipeline that says, here's what you need to do. All you need to do is go ahead and do this copy. So it has nothing to do with graphics. You just want to do very basic copy operations. So you can go ahead and do it over here. And if you click this, you'll be able to see the one thing that you did not see. For example, if you go back to something like lead GPU, you'd see something over here. You would see that we are launching this kernel, which is this kernel, using these parameters. I want you to launch so many threads to basically do the memory copy, right? That's what this CUDA program is saying. In our code, which is Vulkan, you don't see that over here at all, right? The reason for this is because this was automatically deduced, because we were doing a command fill buffer, and command fill buffer is an explicit API that Vulkan offers. So does Metal. So it's a one-to-one mapping over here. And you don't really need to specify stuff. It'll just be taken care of for you. You don't need to specify how many threads you want to launch on the GPU. to do this work. You don't need to do that. So yeah, and I'll show you what happens over here. So if you just go ahead and select this, you'd see something over here, which is effectively 256 threads are being launched directly to figure out how many copies, how many threads do you need to go ahead and do this particular piece of work. So that's implicit, not explicit. And here in the compute pipeline, exactly what is involved. I created the compute pipeline stage, and I can see that it is about, well, let me just try this again. It's about 84 bytes. And then you can also see that this buffer that I allocated, which is only about 1024 bytes, is that, yeah, the buffer that we allocated, which is only 1024 bytes, is what I'm looking for, which is what, 1 CB byte, maybe? No, that's not what actually happens. It's up to the GPU to sort of figure it out because depending on what you're trying to do, it'll always try to make its own assumptions. You're actually allocating 64 megabytes, but that's not exactly what gets allocated in physical memory. This is, you can think of this as a virtual allocation because I mentioned, right? GPUs also have address translation because you have multiple apps that will be using your GPU. So that's what I think this is. And then the 4 bytes that we want to keep writing, the fill value, as it's called, those 4 bytes. And then this is the kernel function. So these are the basic artifacts or objects that you need to effectively do the command copy operation that we talked about. Right. Uh, and here's the best thing. If you really want to know which particular kernel was invoked, because you really didn't write it, right? So for example, in CUDA, this is the kernel. You write it inline. It's the single source method that you use. But in Vulkan, that's not the case. Those two are separate, right? So if you actually went ahead and want to look at it, here's how that sort of works out. This is the actual kernel, right? So this is not the Vulkan shading language. This is basically calling the Metal API, which has its own metal shading language, which is nothing but a variant of C++. And this is what it is. It takes the fill value and keeps each thread takes one portion of the fill value and fills it up, right? Takes 4 bytes. So each thread gets 4 bytes. You go ahead and copy that into this particular clip. And that's exactly what's happening. And then you're saying, okay, these are the thread positions in the grid, all that stuff I'll talk about as we get to the kernel programming part later. So yeah, that's how you can look at it when we talk about debugging this kind of stuff. Basically, when you want to familiarize yourself with how do these things work, etc. The reason I chose the single, wait, let me just increase this. Yeah. The reason I chose a single, what you'd say, command, because it's easier to look at this, right? If I was looking at something else, which is, we're not just talking about what? One command buffer with one compute encoder with one dispatch call. If you are not looking at something like this, and you're new, I mean, this is the first time you're looking at something like Metal Debugger, etc. It'd be a lot of information. Let me see if I can show you an example. So I have this project that I downloaded from one of Apple's sample code things. We just pull that in. So this is effectively um, a hybrid rendering project. So you basically have compute work and some graphics rendering work. So let me just run this and show you what actually happens. So if I just click run it, I didn't even know that you had to create an account in order to be a developer, and etc. And that so that your builds are all signed and all. I'm like, seriously? Okay. So this is the graphics workload that's actually happening over here. So you see that there's some ray tracing stuff going on, all fancy lights. I can turn off the ray tracing and you don't get anything. Then there's ray tracing turned on. You'll be able to see this. Let me show you here. So that's kind of what without ray tracing and with ray tracing. And then there's reflections and stuff like that, which sort of looks like this. All great. I'm not bothered about graphics. But in any case, what I want is I just want to capture this frame, the one frame of, the GPU work contained, the GPU work that you will need to submit to create one frame of that. So let me go ahead and do that. Let me capture one frame. So the moment I capture one frame, you see this is what I get. It's very similar to what you saw previously. Uh, so right off the bat, the command buffer over here is you're packing all this work in this frame into just a single command buffer. You're spinning up, the commands, the way they're encoded into the command buffer. You're spinning up 14 different render encoders and 12 different compute encoders. And then you're submitting about 25 draw calls and 67 dispatch calls. Uh, Dispatch calls are basically all the compute work that you're doing. And then you can clearly see now you're not talking microseconds anymore. You're talking milliseconds is the GPU time frame for this particular frame. It's a 1600 by 1200 frame. Pixel format is that. All of that's great. And then let me see if I can just pull this down. You should be able to see a lot of stuff over here right now. Yeah. So there's a lot of insight that's being provided. I'm not going to get into it. These are all uh, recommendations that Metal is making, saying you may want to optimize this, you may want to optimize that, et cetera, et cetera, et cetera. Some may be reasonable, some may not be, depending on what you're trying to do. So this is an example. Again, if you want to do just click on show dependencies, you'd be able to see the entire, what you'd call, you couldn't see this in our piece because we had one command, but you'd be able to see that there's multiple, what you'd say, compute pipelines, and that means compute passes versus render passes. They're all sort of interlinked. So let's see if I can select one of them. Yeah. So this is a compute encoder. So this information comes in from a render encoder. The compute encoder gets this, and then it sort of there's a signal event over here, etc. So stuff that comes out of here goes in here, blah blah blah, etc. That's kind of what's happening over here. You'd have this visual representation that you can see as well. And like we did in the past, you can see what's taking up for that single frame. What's taking up the maximum compute time? 65% is involved in this one single compute pipeline. You can go ahead and look at that. Yeah, it's ray tracing reflections that's being generated. So apparently there's all the stuff that you need. That means these are the compute resources. There's indirect resources that you're going to be using. I'm not getting into all this because there's stuff like acceleration structures. You see there's a reflection over here. All this stuff needs to be created. So you use all that, you use all this textures and acceleration structures and all of that stuff to do it. And that's what I was saying, when you start, if we hadn't looked at the single command part, this would have been, okay, you'd be a little lost, right? Okay, so that's kind of what I wanted to sort of talk about. And you can also see this allocation sizes for each of those resources that are making up this one single frame. Yeah. And then, yeah, you can also look at what are the bound resources. For this frame, what was actually accessed? Only this much stuff was accessed. Yeah, okay. And then we didn't see this in the previous one, but you can also look at, for this particular pipeline, what was give me some statistics. What was the compute time? What was the memory time? That means how much time did you spend? It says percentage of memory load store instructions relative to the total shader time. So you're executing one shader over here, which is exactly what compute pipeline does. And then percentage of ALU instructions relative to the total shader, you know, total time spent executing the shader. Then synchronization, not much apparently compared to relatively. Control flow time, there's a lot of stuff. Interesting. Yeah. So most of the time you'd want to reduce the load store stuff. You want to increase the compute, the amount of time you're actually computing stuff, because that's exactly what the GPU needs to be doing. You also want to reduce your control flow stuff, that your if-else branches, because you don't want things like divergence, etc. Yeah, so that's kind of what you can look at. And the whole point is, if I was not on a Mac, not using Apple Silicon, let me just stop this for a bit. If I was not on a Mac, if I was not using Apple Silicon, then I could pretty much use other tools that are available to me, which is what I sort of mentioned here. There's RenderDoc, which is an open source tool that you could use if you're on Windows or Linux, apparently. It's much simpler, all right? You know exactly what you're doing over there. With NVIDIA, we've got some proprietary tools inside Compute. People love it because just because only people know that much. I mean, they've been using it alone for a lot. So, yeah. So let's just, I also wanted to cover a couple of other things. So this is from TUVN, is a university, apparently. There's one very good, interesting talk on YouTube as well. I'll probably put links in the description. Uh, Talks about Vulkan, and they go into a lot more detail, or the presenter goes into more detail. But effectively, when we talk about GPU commands that are being submitted to the GPU, they're pretty much of two types: an action command or a state command. As the specification says, the action command is basically commands that actually do work. They do something. Like they do graphics work, they do compute work, ray tracing, or transferring bytes, right? These are all what you'd call action commands. State commands are stuff that, you know, uh, yeah. So let me sort of pull this up. So what happens is, before you can actually do any computational work, you need to set things up. For example, you need to make sure that a very simple thing like your kernel code, the code that runs on the GPU, is actually ready. I mean, it's actually available to the GPU. Then you need to do things like, where are your resources located? What's the format? Are they read and write, or only read or only write? What sort of offsets do I need to be looking at? That is the shader code that you've going to be running. What sort of access does it need to those resources? How are they laid out? All that stuff needs to be communicated as well to the GPU. So you have very specific commands for that. Things like command bind descriptors. So bind descriptor command or a bind pipeline command. All these are very specific commands. So typically in a compute pipeline, what happens is, because we're only talking about pipeline, compute pipelines, you create the pipeline and then you bind the pipeline. The pipeline basically tells you things like, okay, here's the reference to the actual shader code that you're going to be running, and here is the layout of the pipeline. For example, if you are in a graphics pipeline, you have multiple stages that each command should sort of go through. Likewise, in a compute pipeline, there's not much of a difference, because in a compute pipeline, you only have one stage, compute, right? So you'll have a pipeline layout, and then you'll also have some other additional information that you want to sort of pass on. The second thing that you want to do is you have these bind descriptors. We'll not get into bind lists, but bind descriptors are, you've allocated memory on the GPU or somewhere else, and you want to basically describe how to sort of access that and where to find that. All that information is in the bind descriptors set, because you don't just describe one resource. In our case, we did. You normally have a lot of resources that you want to describe. So basically references to metadata about the resources. And then this push constants thing is optional. And then you actually submit a dispatch call. The dispatch call primarily says, okay, here are the number of threads. Here's the so you already know what the shader is. You already know the resources. Go ahead and perform this work. That's uh, that's what the state commands are useful for, right? And then we already went through the demo. We've already talked about profiling, why profiling is important, because you can do event tracking, you can do latency measurements, and the benefits are performance monitoring, debugging, and sort of real-time analysis, right? So yeah, I believe these were the predominant sort of questions, I would say, that you guys had. You guys brought them up, both on the YouTube channel itself and offline as well. Um, so great. I hope this sort of this sort of clears things up. If there are any other questions around either CUDA versus Vulkan or how command processing actually works and how you'd go about debugging stuff and investigating potential issues in your GPU workflow, please feel free to drop a drop a comment with all the different options that you have access to. Although I would prefer it on the YouTube, comment section because it's accessible to everyone else. Yeah. Okay. I guess that's it from my end. Yeah. Thanks. Have a good day.